grade? Ninth grade. Grade, ninth grade. Whoa. Anything above ninth grade? Okay. So let's start. I know you're all here for a math talk, but we have more important issues to address. There we go. Problem number one. How does a person succeed in life? Does anyone have any ideas? Raise your hands and just say something. What do you think is the formula for success in life? Anything? Yes?
Depends on your definition of success.
It depends on your definition of success. Okay. What's your definition of success? Anyone? Let's see.
Yeah, anyone.
Yes?
I will do my best.
Do your best. Do your best, okay. What if something stops you from doing your best? What if, yes?
Try again.
Try again. What if you can't try again for whatever reason? It can be general or it can be specific. So, anything else? Any other ideas? Okay, so the point I was trying to get across is that in order to succeed in life, you will always inevitably come across obstacles that will stop you from trying to do what you want, from trying to do your best, from trying to try again. And in order to succeed in life, we must learn to somehow overcome these obstacles. So how do we learn how to overcome obstacles? Well, this is much easier said than done. The obstacles we'll face will often be obstacles that nobody else has seen before. Or even if somebody else has seen them before, there won't be some sort of set formula for us to abide by in order to overcome these obstacles. So we might be able to ask others for help, but there's not going to be some magical textbook or computer program that will tell us how to overcome each and every obstacle. So in that case, how do we overcome these obstacles? Well, I think we can, yeah, let's see. How do you think we can overcome an arbitrary obstacle? Does anyone have an idea? Okay. Yes, you're not a very active group, that's okay. Let's see. So, I think we can all safely agree that in order to overcome an obstacle, we need experience. We need experience overcoming these obstacles. And by getting that experience, we will be able to build up confidence. Confidence in our abilities to overcome any obstacle that we might come across later. And once we build up confidence, we'll be more likely to persevere when we're trying to overcome an obstacle. We'll be more likely to keep trying, as you said, keep trying, keep working at it until we overcome it. So, in order for this to work, this cycle has to start somewhere. So we gain experience. Through that experience, we build up confidence. Through that confidence, we're more likely to persevere. Once we persevere and overcome the obstacle, we gain more experience, and it goes in a cycle. But in order for this to work, the cycle has to start off somewhere. Now, obviously, we aren't born with experience. We aren't born with the confidence, so we'll have to start by learning how to persevere. Hang on. Sorry. So we'll have to learn. We'll have to start by learning how to persevere. So this is one of the main reasons why. Well, maybe not main reasons, but one of the reasons why your parents might send you to extracurricular activities outside of school, like music or chess or performing arts or sports. And these things are different from what we learn in school. These things require us to work hard at it, to continue doing something. Through these sort of extracurricular activities, we learn that many of the things in life, we have to work hard to get to them. We have to persevere in order to get to them. This is unlike the things we learn in school, where due to time constraints, we don't actually. It's not really a long-term journey to get to it. But the extracurricular activities outside of school, many of them require us to persevere in something in order to succeed. So this starts right around elementary school, and by the time you get to 5th or 6th grade, give or take a year, you'll have pretty much learned to build up this ability to persevere. Yes, so after that, we can start the cycle. Once we know how to persevere, we can start gaining experience in overcoming obstacles. But the problem with that is there isn't an overcoming obstacles class in school. They don't teach overcoming obstacles, and I never heard of an overcoming obstacles extracurricular class either. So where do we find these obstacles to practice on? So my answer is math problems. So math problems are a great way to find some obstacle, obstacle that's low stakes, and put it in front of us, overcome that obstacle, set it aside, get another obstacle, overcome it, set it aside, and build up experience in the process. So math problems are, so you might be thinking, math problems are nothing like the problems that we deal with in real life. And you would be partially correct, but that brings up the question of why we learn math. Sorry. Why we learn math in the first place. So,
sorry, can
yes?
I ask you to remove your obstacle with the chair? Just bothers me.
Sorry. Okay. There we go. Is that better?
You will be more free.
Better? Okay. So, okay. So why do we learn math? You have an answer?
Because our parents tell us to.
Because our parents tell us to. This is often not. Okay. Why? Is your parent here right now? Why did you tell him to learn math?
Everybody has to learn.
Because everyone has to learn math. Why does everyone have to learn math?
The school curriculum.
Because it's in the school curriculum. Why does the school put it in its curriculum?
Because math develop your reasoning skills and the fundamentals.
Okay, so one of the possible reasons is we learn math so that we can function in daily life. For example, when we go to the bank, or we are cooking and reading a recipe, or we're buying things, and things like that. But that's not really all that difficult. Most computer programs can handle the calculations that we need to do in order to complete those daily tasks. So it doesn't really take 13 years of math classes to do that. So that's probably not the best answer. Some might say that math is, we learn math in order to prepare for our careers. And that's somewhat reasonable, but if you look at the statistics, in the United States, only 15% of the population uses algebra or geometry in their daily occupations, and only 5% of the population uses calculus in their daily occupations. And this 15% or 5% isn't even the highest earning top 15 or 5%. They're not the happiest 15% or the happiest 5%. There's some random sort of 5% or 15%. And so it's not very reasonable why schools put it in the curriculum if only 15% of the population is going to end up actually using it. So, a common strategy in math problem solving is to reduce a problem to a problem that we already know how to solve. So, maybe we learn math for the same reason we learn these other school subjects. So, why do we learn English? Why do we learn literature? Any takers? Yes?
So we can talk to each other.
So we can talk to each other. That's actually an excellent point. So we can communicate effectively with one another without getting the other person confused. That's one of the most important reasons why we learn literature. History. We learn history in order to build up a sort of background knowledge so that we can draw out examples whenever we need them in order to support our opinions on current issues or events. We learn biology so that we know what's actually happening to us when we get sick. We learn chemistry so that we know which products that we're buying are good for the environment and good for us and for various other reasons. And we learn physics so that we know that when something isn't moving the way we want it to move, why isn't it moving the way we want it to move? And that all pretty much makes sense. Those are all things that make sense for us to know that will play a large part in our daily lives when we become adults. But then, math, why? So why do we learn math? Nobody seems to be able to give an answer that makes a ton of sense. If you go up to a math teacher in your middle school or high school and ask them why we learn math, they might give an answer, but chances are it's going to be a sort of maybe one of the two answers I gave there, or something that sort of hand waves is like, we call that hand wavy. And maybe your math textbook has some cool applications of what you learn, how those apply to your daily, not to your daily life, but how those apply to various jobs, but those are all very minor issues, and those are mostly things that computers do, not things that we do. So, what is the answer, really? Yeah?
Well, it helps you to develop the ability to do logical reasoning, and help you to develop the ability to look at the problem from different ways and help you to solve problems.
Okay, that's a really good answer. Thank you. We'll continue from there.
Here.
Yes?
I'm just saying, maybe it's what you said, to learn to go through obstacles.
Great, you're ahead of the game already. Let's keep going with this for a second. So, whoops. Sorry. Computer is acting up a little. Yeah. So this is one of the questions where the answer ought to be painfully obvious, but it seems a little difficult to come up with. And whenever you come up with an answer, it seems like you can sort of argue your way out of it. So we'll look at it from an ancient Greek perspective, because the ancient Greeks were the first to actually study math seriously. Okay, so the word mathematics comes from this Greek word here. By the way, is anyone familiar with the Greek alphabet? Is anyone? Yes. This is sort of a side story, but once I went to this math talk, and the professor who gave the math talk wasn't a math professor. He was a ancient Greek historian, but he knew some math because he studied ancient Greek mathematicians. And when but his talk was harder than a lot of the talks by the other math professors I had seen. It was harder for us to understand because he would use letters from the Greek alphabet to label all of his diagrams. And so he would tell us to look at triangle xi omicron phi, and we would have no idea what triangle xi omicron phi was, and it was very confusing. Anyway, that's sort of a, let's see if you do any better. So, do you know what this letter is? Mu, right. And then alpha, theta. This one might be a little harder. This is eta, and then mu and alpha again. So mu makes the M sound, alpha is the A sound, theta is the TH sound, eta is the E sound, mu is again the M sound, alpha is the A sound. This is pronounced mathema, or at least I think it's pronounced mathema. But so you can see that's the first part of the word mathematics. And as you can see, this word has nothing, the definition has nothing to do with numbers. It has nothing to do with logic, logical reasoning. It has nothing to do with shapes. It's just that which is learned. Math is just what you learn. So if you were to ask an ancient Greek, why learn mathematics? If you were to ask an ancient Greek mathematician why learn mathematics, they might say, we learn mathematics for the sake of learning it. Now, admittedly, this isn't a very satisfying answer either. If you were to go up to your teacher and ask them, why do we learn mathematics? And your teacher told you, we learn mathematics for the sake of learning it, you probably would not be very happy with your teacher. But the ancient Greeks were fine with this answer. They were the first people to study math as a subject of its own right, not just for the practical applications. And in fact, that is part of the reason why we learn mathematics. So, but unfortunately, 3,000 years later, teachers seem to have sort of missed the point. For example, so teachers seem to have missed the point that we learn mathematics in order to learn how to learn. Let's keep going here. So what do math problems do? Math problems teach us how to think. That goes back to what this gentleman said. Math problems teach us how to think about something in a creative way, in an original way. Math problems teach us how to take background knowledge, apply it to what we're doing. And math problems teach us how to guess. They teach us how to guess if something will work, and not be afraid to guess if something will work or not. Math problems teach us how to not give up. Back to what I was talking about perseverance. They teach us how to keep doing a problem until we've solved it. This is, in fact, one of the hardest parts of solving a math problem, or any problem. And they also teach us how to give up wisely. So they teach us that sometimes we really do need to give up on a problem. Okay. And these are all very important skills that we ought to learn in order to learn how to overcome the obstacles that we will face in life. But where do we get these math problems? Do we just rely on the math problems that they give us in school, or do we need a little more than that? Well, one of the best sources for math problems, in my opinion, are math contests. Math contests provide, yes?
Could you please give us an example where you give up wisely when you do the math problem?
Give up wisely. I'll actually get back to that in a moment, if you'll be patient. Okay? Thanks. Any other questions? Or okay. Math contests provide problems. They provide an enormous source of math contests provide problems. They provide an enormous wealth of problems that we can take and we can play around with and we can try to solve. And math contests provide a community in order to learn how to solve problems with. Otherwise, if you only learn math by yourself, it can get a little boring. It can get a little discouraging, unless you happen to be really self-motivated. It usually helps to have a sort of community in order to learn math with. And this community and math contests provide an excellent source for this kind of community. Math contests provide competition. Well, this is pretty obvious. And competition is a major part of life just as much as obstacles are. We'll always face competitions in life. We might say we don't like competing, but much of life is going to be about competition. Math contests provide time pressure. I know a lot of people who say that they don't work very well under time pressure. Well, math contests are a great way to remedy that. And they might say they don't work very well under pressure, but after a lot of practice, they eventually get better. I didn't work very well under pressure when I was in 4th grade. I had a friend who was who didn't work at all under time pressure. Most of you heard of the AMC8, right? So when he was in 6th grade, he did not handle the time limits, the 40 minutes for the AMC8 very well. He got a 2 on the contest out of 25 problems. He got 2 of them right in 6th grade. In 8th grade, he got a perfect score. After 2 years of practice, he built up a sort of resistance to pressure, to time pressure. He learned how to operate under time pressure, and any of you students here can too. Math contests are fun. Just learning math on its own, it might not be all that interesting at first, but once you're put into a contest environment with your friends are doing it, your enemies are doing it, and it gets a lot of fun. It tends to get very entertaining. And that's an important element if you want to learn something well. You need to learn in a fun environment, or else you won't be able to grasp the information as well. Now, let's see here. So, as I said, let's see. So, by now, I hope I've more or less convinced all of you that learning problem solving through participating in math contests is a great way to improve your chances of learning how to overcome obstacles in life. Now, I should first point out, however, that the math they teach us in school is not really enough to go to these math contests and to gain what you really want to get out of these math contests. the math that they teach in school, first of all, is too easy. This is pretty obvious. Does anyone disagree with that? I think we can move on with that. Okay, so the math that they teach us in school can get really easy. And another thing is that this goes back to who was the lady who asked me the question about. Okay. Okay. Okay, so I can move on. So the math they teach us in school, it encourages perfectionism. What I mean by that is that they expect you to be able to solve all of the problems that they give you. So when you're taking a math test in school, you're going for 100%. Or at least you're going for, maybe not 100%, you're going for 90% or more. And this isn't really the best way to learn math. When you're learning, it isn't really the best way to learn any sort of problem solving, because problem solving you learn by failing to solve the problem. Once you fail to solve the problem and you find the solution, you can often learn more through failing to solve the problem than repeatedly solving problems that you can already solve. But the thing is, the math they teach us in school doesn't agree with that sort of mindset. The math that they teach us in school, it tries to get us to solve every problem to the point where when we don't know how to solve a problem, we feel like that's our fault, when it really isn't. It's a great opportunity to learn. So this is not a very good attitude to have when facing math problems. It tends to cause kids to give up once they see a problem that they don't know how to solve. And math in school, the third point is that it takes what I call the bag of tricks approach. And what that means is that in school, what they teach is they show you a trick to solve a problem. They teach you that trick. They take another problem, they use that trick on it. They take another problem, they use that same trick on it. Then they leave a list of 20 homework problems that use the exact same trick, and you repeat that trick on all of those problems. And that's the first day of class. The second day of class, they teach another trick. You learn how to do that other trick on all of the problems. And that's boring in that it's once you know how to do a very specific trick, you can just repeatedly do it. It doesn't actually teach you anything. It just teaches you that small, specific trick for that small, specific type of problem. And not only is it boring, it's ineffective. This way of teaching doesn't actually work. When you see a problem that you've never seen before, you have absolutely no chance of solving it because you haven't learned the right trick for that problem. So it doesn't actually work as a teaching method. Also, the learning process is backwards. Again, the math they teach in school, when you learn something, you learn the trick first, and then you see the problem, and then you apply the tricks to the problems. Again, as I said, when the best way to learn, the way for you to learn the most, is to find a problem that you can't do and try to do it. Or maybe not you can't do, but find a problem that is difficult for you to do, try to do it for a while, get stuck, and then learn the right process for it. That makes the trick that you learned, it makes it your own. Because you've worked at that problem for so long already, maybe you've already partially discovered the trick. And maybe you haven't, but you're really familiar with the problem, so that when you see the trick, you're better able to internalize this method of solving that problem. So that's basically how I learned most of my math. I saw numerous problems that I didn't know how to do. I tried to solve the problems first, and then I learned how to solve that. And then I learned how to solve those problems and actually grew to fully understand why that method worked, instead of just receiving a method and saying, go do all of those problems with this method. And one other thing is that the math in school, it follows a very weird curriculum. It goes, I believe it goes, let's see, it goes algebra, geometry, more algebra, a little trigonometry, more algebra, some calculus, and that's it. It completely skips over a large chunk of mathematics, or maybe it doesn't completely skip over, but it barely glances a large chunk of mathematics that's completely comprehensible at the middle school and high school level, which is known as discrete math. And for a lot of you here, you might know that in order to learn computer science in college, you have to know discrete math. In order to learn a lot of different scientific fields in college, you have to have a strong foundation in discrete math. And yes?
What is discrete?
Yes, oh, sorry, apologies. Discrete math is basically, so discrete means separate. So discrete math deals with actual countable objects. So for example, set theory and combinations and permutations, various, let's see, number theory, in other words, about factors of numbers, primes, and topics like these. This is, discrete math is made up, so at the middle school and high school level, discrete math is made up of two large chunks, basically combinatorics. One is called combinatorics, which focuses on counting things. So counting with, so the basic stuff includes counting with Venn diagrams, combinations, permutations, and builds up from there into really advanced counting problems, and as well as graph theory and set theory, and number theory, which is based on primes, factors, multiples, and builds up from there all the way to a very advanced level. But this can be easily taught to students of the middle school and high school level. But schools, for some reason, don't teach this at all. They just stick with their algebra, some geometry, and some more algebra and calculus. They just stick with that path. Did you have a question?
Yeah, when you say math in school, you're talking about the normal track, or you also include both the honor tracks?
Yeah, exactly. So, yes, he just said they're the same thing, and that's absolutely right. So, so in an honors track, it just gives you more advanced algebra or more advanced geometry, and basically you learn it faster. This actually is on my next slide. So acceleration is the strategy that many of you might take. So you skip a year of math, or you skip 2 years of math. But if you think about it, this isn't really solving the problem. If math is going to, if your Algebra 1 class teaches math in a boring and ineffective way, your geometry class is still going to teach math in a boring and ineffective way. If your pre-calculus class teaches you math in a boring and ineffective way, your calculus class is still going to teach you math in a boring and ineffective way. So instead of just going quicker along the curriculum, it might be it is more effective to learn separately from the school curriculum, to supplement your school curriculum with the discrete math I described and a more complete understanding, a deeper understanding of algebra and geometry. Did that answer your question?
I was just wondering if the other track will go deeper or it just faster, it just compact more things into the one.
Generally, from my experience, it usually just goes faster. It doesn't actually go.
If that doesn't go deeper,
It might,
it
yeah.
just compact more stuff. Right. Thanks.
Okay. So, yes. So, how if the schools aren't going to give us enough, how are we going to learn math properly? So I already said that acceleration isn't really the best choice, and so instead of the bag of tricks approach, because in real life, as I said, you're not going to have a specific formula for this obstacle to overcome. You're not going to get another specific formula for this obstacle. It works much better if you know a few basic fundamental concepts instead of 100 different tricks for 100 different types of problems. Does everyone sort of understand that? So instead of learning a bunch of tricks, you learn the fundamental concepts behind why, say, 20 of those tricks work. You don't have to memorize any of those tricks, you just need to know the fundamental concept and grasp that. Well, you can develop your own tricks. Okay? The third thing is that if you want to learn math well, you want equal amounts of algebra and geometry. In school, geometry is only for a single year, and it doesn't go in all that deeply. And many subjects are just simply glanced over. So instead, we take the approach of equal amounts of algebra and geometry and combinatorics, as I said, which is basically counting and probability and things like that, and number theory, which is the study of integers and primes and factors. And and finally, we should learn through solving problems, and sometimes failing to solve problems. Because again, when we fail to solve a problem, when we fail to solve a problem, and then we learn how to solve it, we truly make a difficult idea our own. Okay, so where can we find those resources in order to start learning math in this way? So, other than the contests that I brought up earlier, there are math circles, which are basically, so in our area it would be the Stanford Math Circle. That's the closest. What they do is they give talks every week about some math concept that you wouldn't normally see in school, and you get to explore it on your own. And professional mathematicians who know sort of the way, who are much more familiar with the way college students learn math, which is a lot more like the way I described, instead of the way middle schools and high schools teach math. And this can be an excellent resource. And school math clubs. Most schools have their own sort of math club. If you're in a middle school, you can check out your school math counts program. They usually, actually, I'm not. Yeah, so most schools should have their own math clubs. And these provide, again, what I said, they provide a community. They provide friends and companions who are also learning math the way you are, and you get to share resources between yourselves. And finally, there are contests, which I will spend the next few minutes describing. one of the, I just mentioned this, one of the popular contests at the middle school level is math counts. And how many of you have heard of math counts? He's wearing a math counts shirt. Could you stand up by any chance? Yes, thank you. Yes, math counts, that's, yes. That's a contest for middle schoolers, 6th through 8th graders. The format, there's, you can read that if you want, but yeah, it has a sort of complicated format. And the material it covers are middle school level algebra and geometry, as well as introductory combinatorics and number theory, which is, which I just talked about earlier. And math counts is great. The advantages to math counts are that we have you can generally find a large math counts community at your school, and because a lot of people take this contest, a lot of middle schoolers take this contest, and you can find plenty of resources to practice for math counts because it's such a widely known contest, and there are all these different formats that put you in different environments, different situations for contest taking that sort of reinforce the material that it covers. The slight disadvantages are that we're currently sitting/standing in the hardest math counts chapter in the United States. So this tends to discourage students somewhat. In most, the scores that we need in our chapter to make states to make the state level are the scores that are higher than the scores that that other people in other chapters need in their states to make national levels. So that might discourage some students because, first of all, you have to get on your school team. You have to be the top 10 in your school in order to get there. But if you're willing to work hard enough, that's entirely possible. And another problem is that this only comes up when you've taken math counts for a couple of years already. You want to be careful that when you're practicing, you're still coming up against problems that are difficult for you. Problems that, so you can see that the sprint round, which is one of the rounds of math counts, it gives 30 problems in 40 minutes. So that's less than a minute and a half per problem. And that can get really tough. And what math counts often becomes is, you know all the material already, and you're just repeatedly practicing in order to get under that time limit. And that's not really the most effective way to learn math, because that's not really teaching you math. That's teaching you how to do math contests under a time limit really quickly. And so that it doesn't become about learning how to do math problems anymore. And you want to try to avoid that in order to, because that's not a very effective use of your time. Okay, but otherwise math counts is great. So before you've had a lot of contest experience, math counts is a great way to build up that contest experience, especially if you're in 6th or 7th grade right now. AMC 8 is for 8th graders and below. That's why it's called AMC 8. And 25 problems, 40 minutes, no penalty, multiple choice. The material it covers is slightly easier than math counts level, actually. It covers basic algebra, geometry, combinatorics, and a tiny bit of number theory. And the advantages are that it prepares students for future AMC contests that I'll talk more about. And because usually as middle schoolers, students don't really have that much opportunity to actually take contests in a contest environment unless they make it to the top 10 students in their school math counts team. So this provides an opportunity for all middle schoolers to take math contests and get that practice. And it also takes place early in the year. This takes place in November. Most of the other contests on this list take place in the latter half of the year. So this gives something to prepare for during the start of the year. And the problem is that the problems are only slightly challenging. The problems are better than problems are better written than the problems that you would see in school, but they are still not that challenging if you get enough experience. But they can still present a pretty good challenge for most students, temporarily. AMC 10 and AMC 12. AMC 10 is for 10th graders and below. AMC 12 graders AMC 12 is for 12th graders and below. And the format is 25 problems, 75 minutes, and SAT-style penalty multiple choice. And what this means is that the multiple choice penalties are designed so that if there are 5 answer choices, if you guess, it's to your disadvantage, but if you eliminate one of the answer choices and you guess, it's not to your disadvantage. I can talk about that later if you have questions about it. Anyway, so the AMC 10 covers introductory and a little intermediate algebra. It covers geometry, and it covers introductory geometry, combinatorics, and number theory. AMC 12 covers some more advanced algebra, some intermediate algebra and combinatorics, and still pretty introductory geometry and number theory. The advantages of AMC 10 and 12 are that they are non-routine problems. They are not, well, most of them are non-routine problems that aren't like the problems that we see in school. There's no straightforward method that we can just immediately see how to solve the problem. We have to think about it for a bit. It's well timed, 25 problems, 75 minutes. It's a pretty good timing. So you don't feel too rushed like on the in math counts, and it's not, but it still provides enough time pressure for you to practice how to handle time pressure. And it covers a lot of good material, as you can see here. It covers half of it is in discrete math instead of a tiny fraction of it like in school. And there's plenty of practice resources you can easily find, and you get 2 chances per year. And I think some colleges like to see them on their applications, but I don't really worry too much about that. But that might be interesting for some of you. Okay, so the AME is the next step on the AMC level. The top 2.5% of the AMC 10 high scores and the top 5% of the AMC 12 high scores gets to take the AME. It's 15 problems and 3 hours, which should give you a chance to see how hard those 15 problems are. And it's not multiple choice. It's all problems are an integer answer between 0 through 999. If you get that integer, you get the problem right. If you don't, you get the problem wrong. The material it covers is, intermediate level algebra, geometry, combinatorics, and number theory. So it's quite a bit harder than both AMC 10 and AMC 12. The advantages are that it provides deep and challenging problems, and it gives you a lot of time to sit there for 3 hours and think about deep, challenging problems. And it covers excellent material. It covers all of that material, and there's plenty of practice resources. And I can't think of any disadvantages, which should be a good thing given the amounts I've criticized other things during this talk. Okay.
I have a question.
Yes.
For the MC 10 and 12, where can we find some good practice resource?
I
know some LPS, etc.
yes, AOPS is basically where you find practice resources.
Is there anything else?
That's usually enough. Is that not enough for you, or are the AOPS tests not enough, or
Where
If
do
you
you
use
learn
it-
your math?
sorry, what?
Where do you learn your math?
I got it all from AOPS. Mostly
AOPS.
from AOPS. Yes. In fact, I'm going to talk about AOPS very soon. So hang in there. USAMO/USAJMO. That's the next level. The top 500 AMC 10/12 and AMY high scores get to take this. It's 2 days. You get 4.5 hours per day, 3 problems per contest, and it's really fun, actually. I took this contest for the first time earlier this year, and it was a really great experience, even though, yeah, it was a really great experience. It's proof-based, which means that you write proofs for the problems. Now, this is very good practice, and the other contests, none of the other contests give opportunities to practice writing proofs, but writing proofs is, especially under a time limit, is a great way to sharpen your communication skills. And in fact, I was actually talking to my mother earlier about this during the day, and it was that I found myself faster at writing timed essays in English class because I had so much practice writing proofs for math contests. And yes, and so it gives you a great chance to sort of develop that logical reasoning, because if you can write a proof for a problem, that means that you fully understood how to solve that problem. It means you completely grasped that concept. And but the interesting thing about USAJMO and USAMO is that the material it covers is actually pretty on the same-ish level as the AMY, except because they're all proof problems, they just get so much harder. Anyway, yeah, so those are the contests. There are some other contests here. There are some, all 3 of these are mostly for high schoolers, but can also be for middle schoolers. And I put all of these on here because, as I said, the USAMO and the USAJMO are the only other contests that practice proofwriting. These contests all practice proofwriting, and you don't have to sort of compete before you get into it. You might have to compete a little for the ARML, but for these 2, you don't have to compete to get into it, but you also get proofwriting practice in the process. And I can talk about these later if any of you are interested, but I'll skip mostly over these for now. Yes, now, so what can parents do about all this? I've talked about all of these contests and stuff, and what can parents do? So they can pay for books and classes. I'm going to recommend some books later. So, yes, so if your student wants a great math textbook, you should pay for it. If the student wants a great math class, you should pay for it. Never get in the way of contests. If a student wants to take a math contest, you shouldn't get in their way. Also, parents should encourage students to take math contests, but obviously they can't force students to take math contests, because learning from math contests really only works if you're interested in taking that math contest. So give them encouragement. And number 4 is one of the most important things. Actively communicate with other parents and share resources among them. Usually in any middle school, for every grade level, there's that one parent who has the email addresses for all of the other parents of students in the math club and sends them emails whenever there's a math contest going on, or whenever there's math contests going on, or whenever there's a good math class that they found. and whenever they want to set up a meeting for the math team, and find that parent and get on their email mailing list, or better yet, become that parent. Yes, okay, and then finally, teach with caution. So you might be tempted to teach your children how to solve various problems, and that's sometimes effective if they've been working on a problem for a long time and they get stuck with it. Parents are sometimes a good resource for figuring out why the student got stuck. But you want to, if you're ever going to teach a student, you want to actively communicate with them in order to make sure that they get the fancy things that you're doing with the problem. Make sure that they understand exactly what you're doing. And one thing that often comes up with parents teaching students how to do a problem is that I'm sure many of you have experienced this or seen this before, but when your student was in elementary school, they might have had one of those problems where it could easily have been solved through basic algebra, but their teacher or themselves insist on guessing and checking in order to find the answer. Do you get what I'm talking about?
Yeah.
You've seen that happen, right? You've definitely seen that happen. Okay, so what happens is that, so what happens there is that algebra is a very important topic. Your children should learn algebra, but they will eventually learn algebra anyway. But there aren't that many opportunities for them to learn how to guess and check. Guessing and checking is a very important skill in life. If you look at what an actual mathematician does, much of an actual mathematician's work involves guessing and checking, except they're not guessing a number and plugging it in, they're guessing a method and trying that method and seeing if it works, only to see that it doesn't work and guessing another method, and so on. Actual scientists always use guessing and checking. Businessmen use guessing and checking. It's an important skill to know in life, and it begins by guessing and checking on these small problems and getting the hang of it, and not being afraid to guess something in order to see if it works. But once you teach the skill to them, and sort of ruin their chances of guessing and checking the problem, you've sort of taught them that given a problem, they should know the trick to solving the problem instead of blindly guessing and checking. It sort of turns the students against guessing and checking, so that once they come across a math problem that they don't know how to solve, they're scared of guessing to find it. They just get stuck because they've never practiced how to guess the solution method to a problem. And they can learn algebra anyway. They'll learn algebra. Okay? So that's sort of one example of what I mean by teach with caution. Okay. Yes, books, art of problem solving. Yes, this is my books slide, and it consists entirely of art of problem solving, because art of problem solving books are a wonderful resource. And I'm wearing an art of problem solving shirt right now to demonstrate this fact, and I'm not getting paid to do this. And what these books do is that they follow that format that I just described. They follow the problem first, try the problem, get stuck on the problem, see the solution, try the problem again, actually learn the concept. That's the format that you want to go with when learning math. And art of problem solving books, they follow this format, and they follow this format really well, so that you actually fully grasp all of the concepts that you're reading about. They are the only textbooks I have seen that work as stand-alone teaching materials. What I mean is that you can just read the textbook, even if you didn't know anything about the subject beforehand. You can read the textbook, and then after finishing the textbook, you can fully understand the subject without or with very minimal help from a teacher or a parent. And of course, that requires the student to be extremely self-motivated. But yeah, so in other words, these books are a wonderful resource. So the four things, I talked about the four areas of math that you want to concentrate on. There were algebra, geometry, combinatorics, and number theory. Art of Problem Solving has an introductory book for all four of these, and they have intermediate level books for algebra and combinatorics. And they should be coming out with other books soon. And they also have a pre-calculus book and a calculus book, and both of them are really helpful, and they are part of the reason why most students in this day and age succeed on math competitions, because they're just really great books. Yes. Okay. So and they have a lot of good problems. They provide a lot of challenging problems at the end of each section that aren't just repetitive. Apply this trick again problems. Okay. So what can students do? I just saw one parent tapping their student on the shoulder to pay attention. Okay, what can students do? Practice. Don't be scared. That's one of I tried to get this across when I was talking about guessing and checking. Don't be scared to try something on a problem, even if you don't know that it will work. Don't be scared to try listing things out, even though you've been discouraged from listing out all the possibilities. Don't be scared to try it if you're completely stuck. And don't be scared to see like this really challenging problem. Maybe you can still, if you work at it for a while, maybe you'll get somewhere. Don't let it scare you. It's really important. Okay. Again, practice. Practice efficiently. So as I mentioned, the Art of Problem Solving website also contains a lot of resources. It contains a lot of practice contests from past competitions, and the problem is I believe it's the AMC 10 contest. You can actually get through those pretty quickly. So also, I think also the AMC 8 contest. So practice in an efficient method. Don't just, taking 5 contests in a row isn't going to help you learn all that much. It's better to space out taking these contests to practice, or taking these contests afterwards when it's closer in time to the actual contest. And in that way you practice efficiently. That way you don't run out of practice materials. And also if you, yeah, that's basically, yeah. Okay, stay organized. This is mostly when you're actually taking a math contest or trying to solve a math problem. It's even if you're not an organized person physically, be an organized person mentally, and be an organized person while taking math contests. I am not a very organized person when it comes to my possessions, but when I'm taking a math contest, I know that it's important to keep my work organized. That's actually very helpful. That prevents you from making any sort of mistake. It makes it very easy to go back and check your work. It also makes it very easy after the contest to go back and see what you did wrong, see which areas you can improve in. Stay organized with your work. And practice. Practice more. Practice. So whenever you find, whenever you're looking for something to do, try a challenging math problem. It can actually be very fun. Talk about math. As I said, find a sort of community. If your school has a math club, join the math club. Talk about math with your friends there. If your school doesn't have a math club, Art of Problem Solving also has a math forum where you can talk about math problems with people from across the nation, across the globe. And rehearse, which is another word for practice. Never waste an opportunity to learn. And what this means is that, again, so if you're in some sort of math class or you're reading a part of a math textbook and something confuses you, that's a very good opportunity to actually get familiar with whatever confuses you. Find help. Get help until you're not confused by that subject anymore. If you don't get help when you're confused, once the class builds up on that stuff, you'll get even more confused, and the confusion will just sort of pile up, all because you wasted that opportunity when the confusion was really small and you didn't ask for help at that point. And there's a lot of other examples of not wasting opportunities to learn. But yeah. Okay. What can I do? As in me. Okay, so where's Sherry? Let's see, in her room. Okay. Let's see, is she busy or? Okay, so.
讲完了哈。
这不快了，我讲我课的事。
啊，就讲课。对。
Okay, so I am going to start a class here. This Saturday or next Saturday?
I think it's better
Next
next.
Saturday.
Yeah.
Okay, next Saturday. So not the coming Saturday, but the Saturday after that. It'll be 2 hours per week, and it should go all the way until the first AMC 10 contest. Right?
AMC 10 is the next.
November.
February.
Yeah,
AMC 10
AMC 8
is
is-
February. AMC 8 is
February.
February. Yeah.
Mm.
So I'll try to go all the way until February, and what the class will cover, I actually didn't expect so many people to come. I expected a small number of people to come. But anyway, I'm going for a more personalized approach to teaching, to training students in math contests. So this might be difficult, it might be a little difficult to do, but I'll sort of tailor the class to the interests of the students. I've constructed a survey for, if you want to register for the class, I've constructed a survey for you to fill out what your sort of goals are for learning mathematics. And I hope what I've talked about so far sort of helps you develop those goals. And even if you don't have goals yet, that's okay, because I'll sort of help you with them. And basically what I'll be doing is I'll cover a balance between the 4 subjects I mentioned: algebra, combinatorics, geometry, and number theory. I'll focus on 1 or 2 topics every class, and I'll provide supplemental homework problems that will actually be challenging problems every week, and I will maintain contact with each student by email so that they can get help with the homework problems. And in addition, I'll provide various resources in order to patch up, because it's impossible to cover all 4 of these areas with very rigorously in only the time that we have from now until February. So I'll provide resources where they can patch up on subjects that they still need to build a foundation on, but then each class will cover sort of selective material that really applies to solving problems. Do you sort of understand that? And I'll sort of I'll tailor the subjects I'll be covering each day to the interests of students.
Nelson， 要不要现场讲一道题
Yes,
？AMC
I
8
have
考的
that
比较难
prepared.
的，然后 AMC 10比较容易一点的。OK， great。
I'm gonna go with this poem because I am running later than I thought I would be, but that's okay. So,
How about student read the
let's everyone read this poem first. I'll give you, so AMC 10, remember there are 75 minutes for 25 problems. The first 10 problems, if you manage it correctly, you can solve each of them within 2 minutes or less. So that gives you another 55 minutes to do the remaining 15 problems. And then you don't have to finish all of those problems to get a satisfying score. So in the end, it adds up to, when you get to problem number 23, you usually have if you manage your time correctly, you have 4 or 5 minutes to solve the problem. So usually you'll have you can spare yourself a minute to just stare at the problem and think about it. Read it once, read it again if you don't understand it. Yes.
Is the answer C?
We'll see. Okay. Let's see if you're right. Okay. So, does anyone have any ideas on how to approach this? Well, yes?
The width is x and the top is x root 3.
Okay. So that's one way we can approach it. And so one of the things I'll be focusing, I usually focus on when explaining a problem, is how to make life easy for yourself. So how to solve the problem in a way that makes things really simple for you to do. That makes the actual calculations really simple for you to do. Yes, yes, we can assign this to be x and this to be x root.
If you want to make it easier, make it 3x.
That's,
You want to make it easier 3x because they divide it into 3.
right, so we want this preferably to be a multiple of 3 so that it's easier to divide into 3 parts. And so if this is 3, let's say the length of this is 3, then what would the length of this be?
Root 3.
Root 3, right. Because the length is root 3 times the width. Root 3 times root 3 is 3. Okay. So now, we assigned it to be 3 so that when we divide it into 3 equal parts, it gives us an easy number to deal with, 1. Okay. So now, what might be helpful to know at this point?
Area.
What's some information that we might be able to get? The area, that's something really simple, and it asks for that in the problem. So let's keep track of this. The area of a large rectangle is 3 root 3. Right. Okay? Now, what's something else? Do you notice anything? I know you noticed something. Do you notice anything about how this line is drawn? I know you noticed something. I'm waiting to see if anyone else notices something. Okay, what do you have?
Areas are equal the way they're divided.
The areas are equal. That's a good point.
You can rotate this overlap to 2.
That's another good point. But what we want is when we're folding it along. So when we're folding it over, are they going to overlap?
No.
Yes.
No. They're not. I mean, yes, they are going to overlap, but they're not going to perfectly overlap. As you can see, it's going to have some stuff hanging out here. So what we really want is to figure out how much stuff is hanging out. Yep.
So like when you fold it, you take out that triangle.
Okay.
Yeah, connect that to the.
So I fold this over. Yes, so I'm going to form some sort of triangular overlapping region. Okay, so, but do I know anything about that triangle? Yes. Sorry, what?
1/6.
Who's 1/3?
Oh, I see what you mean. I see what you mean.
Oh, yeah.
Okay, so how do you know? Okay, we suspect that when we fold this over here, given the way the diagram is drawn, this point might coincide with this point, correct? That's what you're suspecting? Because you said that you get this triangle over here, right?
You're saying the small triangle on the left is 1/6. Yeah.
That is correct, yes. But do we know that when we're folding along this line, this point hits here and it actually forms that triangle? Not yet, not yet. So let's take a look at this triangle for a bit. Well, we don't know anything about where this point is going to meet this side. So we don't know anything about this side of the triangle. And we don't know anything about how far this length is going to cover here. So we don't know anything about this side of the triangle. But what about the third side of the triangle? In other words, what about this length? How can we find this length? Did you say something?
It's 2, right?
It is 2. How do we know?
This is a 30, 60, 90, right?
Exactly. So we can build this right triangle here. The height is root 3. Sorry. Yeah, the height is root 3. And the base here is 1. So what's the hypotenuse? 2. Because 1 squared plus root 3 squared is 4. Square root of 4 is 2. Now wait. Where else do we have 2 on this? We have 2 here, and we have 2 here, right? And you just said it was a 30, 60, 90 triangle. And we know that because this is twice the length of this. So, what does 30, 60, 90 triangles make us think of?
Equilateral.
Equilateral triangles. So, because this is the 30, 60, 90 triangle, we know that that's 60 degrees, that's 30 degrees, so this is 60 degrees. That means that once we fold this side over here, it will hit over here because there is another equilateral triangle here, right? So when we fold these over, 2 equilateral triangles work. Does everyone see how that works? Okay. So now, by the way, I'm going to step out of this for a moment to say that this is a common strategy for solving problems. Watch out for things that you're familiar with. You're not familiar with this weird shape here, but you are familiar with 30, 60, 90 triangles. Look for shapes that you're familiar with. And if they aren't there, draw lines to create them. Okay. We fold this over, we get this piece moved over here, right? And this triangle here disappears on top of this triangle. So we can move this piece back over here, and we can simply delete this part of the triangle, and this gives the same area, right? Okay, so now what we're worried about is how much of the rectangle we deleted. So how much of the triangle, what did you say? How much of the triangle, how much of this triangle is the entire rectangle? 1/3. Because if you divide this in half, you can simply move this over here. And these three are equal rectangles. So the answer would be 2/3. 1 minus 1/3, 2/3. And you're right, the answer is C. Okay. I took a long time to explain that problem for a reason, which was so you can understand sort of the thinking process that you would have to go through to solve a problem like this. I normally don't take that long to explain a problem, but that's just an example. There's another problem. Okay. This is much more interesting. This is also interesting. Okay. I'll give you a minute to read this. We'll share our thoughts. Okay. By the way, did anyone have any questions on the previous one? No? Okay, good. Okay. So, any thoughts? Yes?
Between any two consecutive powers of 5, there are either 2 or 3 consecutive powers of 2.
How do you know that?
Because like simple testing, just observe it. Like you can list out the powers of 2 and 5.
Have you seen this problem before?
Yeah.
Yes. Please don't give it away if you've seen the problem. Thank you. I would appreciate that. Okay. So, okay. So we've seen this. We saw this, and we don't really know how to deal with this because it's kind of a weird problem. First of all, the first sentence is really weird. The number 5 to the power of 867 is between 2 to the power of 2013 and 2 to the power of 2014. How does that even help us? We don't know. Okay, so let's ignore that for now. And let's focus on the second part. How many pairs of integers m comma n are there such that 1 is less than or equal to m is less than or equal to 12, and 5 to the n is less than 2m, 2 to the m is less than 2 to the m plus 2 is less than 5 to the power of n plus 1. Does everyone understand what this statement is trying to say? So, in other words, you have some number, you have some power of 5 here. You have some higher power of 5 here. And 2 to the m, what's 2 to the m plus 2 in terms of 2 to the m?
4 times 2.
4 times 2 to the m, right? So that means 2 to the m is between 5 to the n and 5 to the n plus 1. So is 4 times 2 to the n, and so is that number in between 2 times 2, right? So there's 3 powers of 2 here. Okay, so we just need to count how many times that happens. How many times at least 3 powers of 2 appear between 2 powers of 5. Okay? Now, how do we do that? It doesn't seem like a very easy task. So let's start listing. Let's start small and start listing some examples. That's often one of the basic starting points you want to do when dealing with a problem that you have no idea how to solve. Especially here, when it's really easy to see what small examples to try. So what's the first power of 5? 1. What's the first power of 2? It's also 1, but we'll just, yeah, the next power of 2 is 2. It's the next power of 2. And then so on, right? Okay, what's the next power of 5? What's the next power? What's the next power?
125.
125, and then there's a 128 here. Okay. Okay, so it looks like, let's see. How many are there between these 2 powers of 5? Oh, sorry. Okay. How many are there between these 2 powers of 5? How many are there between these 2 powers? Okay, so it's giving us 2 every time. But here there's clearly 3 powers of 2 between the 2 powers of 5. So, are there any that are?
Yeah, next one.
Next one. Let's try the next one. Let's see. 125. What's the next power of 5? 625. 128. 656. 512. 1024. But that's on this end, right? So there's 3 here. And that's good. That gives us 1 of these. We just need to count all the rest. And clearly the answer choices tell us that there must be some. In fact, there's quite a few. There's at least 278 of them, maybe more. Okay, is there a pattern? You said there's probably a pattern. In these kind of problems, we're looking for a pattern. So we don't really see any discernible pattern, but yeah, okay. So we have 2 here, 2 here, 2 here, and 3 here. Could we have any other amounts? Powers of 2. Let's play around with this thing. Let's say we had 4 powers of 2 between 2 powers of 5. Okay. So in other words, we have some number x, which is a power of 2. 2x, 4x, and 8x. These are the next 3 powers of 2, right? Okay? So all 4 of these are in between powers of 5. And I'll just write y as the power of 5, and then the next power of 5 is 5y. So we have some inequality like this. Okay? Is this possible?
No.
Why not? Can anyone disprove this? Yeah?
Because if x is greater than y and you multiply y by 5 and 8 by x, 8 is greater than 5.
Y is less than x implies that 5y is less than 5x. But here it tells us that 8x is less than 5y, and that gives 8x is less than 5x, which is a contradiction. Does everyone understand that? So what does this tell us?
So between every power of 5 is 2 or 3.
There's 3, 2, 1, or 0. That's what it tells us, right? We have to be careful. We can't automatically eliminate some possibilities. Okay, so there's either 0, 1, 2, or 3. We've only seen examples where there are 2 and 3. And so we want to look for some examples with 0 or 1. And we want to see if there are any. So we can try the strategy again. So what sort of inequality should we write? start with the power of 2, we're worried about. And let's say there's only 1, because we already know there could be 2 or there could be 3. Let's say there's only 1. So this is trapped between 5y and y, right? How should we express the fact that there's only 1? I want new hands. I want... Okay, so think about it. If there's... If the next power of 2, let's consider 2x, right? If this power of 2 is not... Well, can this power of 2 be between these two, if there's only 1? No. So instead, we want this outside. We want this right here, right? Okay. So, and what about on this end? The other power of 2, the power of 2 previous to this one, should also be outside the range of the y 5, right? Does everyone understand that? Okay. Fractions are difficult to deal with, so I'm just gonna, if you can see, this is still the same statement. X is still a power of 2, and these are the powers of 2. So if you only have one power of 2 here, is this possible? Let's think about why it's, you shook your head, why isn't it possible?
Well, because x is less than y, so therefore 4x is less than 5y, not greater.
Right. So, exactly. So, x is less than y. So, you said, so 5x, you said 5x is less than 5y, right? But then 4x can't be greater than, so that's a contradiction. So there can't just be 1. And by the same logic, there can't just be 0. So by the same logic, there can't just be 0, because that would mean we had something like this. And if 4x isn't big enough to be above 5y, then 2x definitely isn't. So that means, as he said here, there are only 2 or 3 in between the powers of 5. Okay, that's some progress. But you wanted to look for a pattern, right? This isn't really a pattern. This tells us that there's either 2 or 3, but it doesn't really tell us where the 2's and where the 3's appear. So we're sort of stuck here until we look back at the problem. Whenever we're stuck, we want to look back at the problem and see what we haven't used yet. So what haven't we used yet? Yeah?
The first sentence.
Yeah, the first sentence. Okay. So we know that 5 to the power of 8, 6, 7. This is between 2 to the power of 2014 and 2 to the power of 2013. Now let's think about, for a moment, what that tells us. We're concerned with the pairs of powers of 5 that have 3 powers of 2 within them. So we have a bunch of these intervals of powers of 5. And we want to see which of them have 3 between and which of them have 2 in between. Okay, so let's just say, okay, let's think about this. Before, we found an example where there were 3 in between, but can we sort of work backwards from here? Let's say we didn't know that that possibility was there. Let's say we didn't know that there could be 3 in between. Then, is there a way to show that there must be 3 in between? Let's think about this. So from 5, let's say from 5 to the 0 to 5 to the 1, there were 2 powers of 2. from 5 to the power of 1 to 5 power of 2, there were 2 powers of 2. And there were still 2 powers of 2, and still 2 powers of 2, and so on. All the way up to, well, we have this 5 to the power of 867 here, so why not use it? 5 to the power of 867, 5 to the power of 866. There's still 2 powers of 2. So 2 to the power of 2013 and 2 to the power of 2012. How do we know that this isn't the case? Why can't there just always be 2 powers of 2 in between each interval? Well, how many of those would that give us? How many 2s are there here? If we go all the way from 0 through 1, all the way up to 866 to 867.
0.
How many powers of 2 are there? Would you say?
Wait, no.
Let's see. So
2013.
No. Oh, I see what you mean, but that's sorry. So there's if there's 2 between 5 to the 0 and 5 to the 1, and there's 2 between 5 to the 1 and 5 squared, and there's 2 between 5 squared and 5 cubed, all the way up. There's 2 between 5 to the 866 to 5 to the 867. How many 2s are there?
1,734.
1,734. You got that by multiplying 567 by 2, right? Because this top one is 1. This is the second one. This is the 867, right? This is the 867th interval. There's 867 2s. So that means that we have 1,734 2s. Why do we know that's not the case? Yeah? Right, the first sentence. This is between 2 to the 2013 and 2 to the 2014. If we only went up to 1,734, this is nowhere near 2013. In fact, how far is it from 2013? Let's just see.
The answer.
279.
It's 279. Hey, 279 is one of our answer choices. Did we just suddenly find the answer? Why is this? Why is this the answer? Can someone explain it to me? Yeah. Right, exactly. Because we know that these are either 2s or 3s. And if we assume all of these are 2s, it only gets us up to 1,734 powers of 2. So if we want to get all the way up to 2013 powers of 2, we need to have somewhere in here 279 extra powers of 2. But how come we know that there aren't 2 that are in the same interval? Well, we proved that. We proved that all of them are either 2 or 3. So that means all 279 of these extra powers of 2 must go in different intervals. So how many intervals have 3 powers of 2? 279. That's what the question asks us for. Any questions about that? This was a really difficult problem, by the way. This is number 25 of the AMC 10A. This was the hardest problem on the contest. Very few cases bonus. But in fact, all we relied on here is just listing out a few examples and just playing around with it in our head. And really, this is the basis of problem solving. Just taking a problem, playing around with it in our head, and then formulating a strategy of attack, or just happening upon some idea. And this might seem magical at first, but eventually, with enough practice, you'll be able to grasp how to do this. Thank you. About anything. It could be about problems, it could be about anything I've spoken about today. Yes?
What's your username?
That's an odd question. Okay, I can give that to you later. Why do you want it?
I have an account too.
Okay. Oh, I can give that to you later. Any
我们
other?
这里还有一个很厉害的哈，也是一个 USAJMO 和 JMO 的那个 Andy 看，呀，可以 ，yeah, you can say some more.
So what is your content of your class? Like say you give a bunch of problems to
Basically,
people.
yeah, so I'll start off with a problem, and the problem will introduce a sort of concept, and by like working at the problem, they'll be able to sort of develop a sort of basic intuition about the concept, and then I'll go over the concept in more depth, and then they can practice. Yes?
How do you then solve the problem? You read books or you how do you then
I also, read art problem solving books, take classes.
take class?
Take classes, yeah.
In school or
Not in school, as I said. Yeah, so some of it is from past not past, but just older problem solvers. They are usually sort of best resources, best like hands-on resources for problem solving. There's Art of Problem Solving also offers its own classes online. Some people like them, some people don't. I happen to be one of the people who are okay with the online classes, but it's not really the best format for everyone, but yeah.
呀，他那个 Nelson 是去年 last summer 就是刚刚读完8年级，要读9年级的时候，就是在我们这儿开始教 MC， 教得非常好。那这个小男孩站在门口，这个是他的学生哈，他家离这里过来开车要过来2个小时哈，这么远跑过来哈，跑过来来上课，非常优秀哈。大家不要小看人年轻，所以他
现在几年级？
现在刚上10年级，刚开学几天了？2星期，3星期，对，对，那个我们这里有很多优秀的高中生哈，那个 Andy 也是很优秀，是 Limburg 今年 senior 哈，所以说不今天把他也请来，就是他也是很USAJMO，以前10年级就是 JMO 哈，10th grade 是 JMO，然后他是junior 的时候是考的USAJMO，现在 senior 还没考。到明年才考哈。如果大家有什么，他也有一些自己的感想，就是考那个，但比较高 level， 就是其实 Nelson 现在也是JMO了哈，他9年已经JMO，也是很厉害的哈。就是如果说我想 Andy 也可以，因为我那天跟他谈的时候，他也跟我讲了一些他怎么样解A米题的一些感觉，你可以分享5分钟，然后一起 Q&A 都可以。
Okay, so I'm Andrew. I'm a senior at Limburg. Like shares everything with me. So actually, I'm most likely going to be teaching the AME class, and there's something about the AME that's not quite like the AMCs, and it's mostly shown through the name. And so, do any of you know the acronym for AME? Yes, American Invitational Math Exam. Now the most important one is this one, invitational. So basically what this means is you're invited to take the AME, and what that already means is that like you've done really well in the AMC, you've proved yourself basically. And it also basically tells you something about the AME. It's an invitational exam. It's not like it becomes more different in that the topics, like I think Nelson's covered this, it's mostly algebra, geometry, coming towards number theory. It's this mix of these 4 like main pillars. But the invitational part makes it more different. Like instead of just, I think Nelson's also covered this, like having a bag of tricks for school, the AME is really about how to solve problems. And it's basically, you're most likely not going to get it on the first glance, sort of kind of problems. I'm not sure how to describe it, but it's like, it's not like the school problems where you look at it, it's like, okay, I've got this. This is easy. AME problems are more, you have to get the right direction. Where I think Nelson can also attest to this, where it's not the first step that matters, or the second step, or the third step. It's all of the steps. You have to have a vision. You have to try things. You have to be creative to solve these kind of AMY problems. And this is actually what makes AMY so powerful and like in a resume, is because it's basically proof. Look, I have been invited. I have basically it tells people in colleges that I am dedicated to math. I have the potential for creative problem solving. And for those of you who solved this 2014 AMC 10A25, which you all have, I strongly encourage you to at least consider taking an AMY class, mostly because the benefits of doing well on this is basically the proof that, hey, I'm interested in math, I'm a creative problem solver, I can survive and like basically survive through hardships and continue, and I have persistence, and it tells a lot more about what kind of character you are, and like it's one of the best competitions to take. Yeah, that's. Would you like to say anything about it?
You won. Well, these are some AMY problems. If you
Yeah.
want to see them.
Okay, so go for one of them. Should we choose one to go over real quick?
I mean, I feel like this is supposed to go till 9, right? I didn't expect it to take this long.
Yeah.
But anyway, first of all, do you have any questions?
How will you teach the class? How will you teach the class?
Oh, for the yes. So I basically just went over that. So what I'll do is I'll present a sort of problem that that gives students a chance to think about the problem for a while, and then it'll probably be a harder problem than the ones they'll see in the AMC 10, and then we'll go over that problem, and then that will illustrate some important concepts that we'll sort of think about and play around with and see what other problems we can use that concept to solve. And also, I will provide sort of some supplementary material that will patch up any fundamental subjects that they still need help on. And yeah.
Okay, so I can answer this question as well for my AMY class. So basically, so I have a plan for the first 4 classes. I'm going to be going over the 4 basics, which I've already mentioned: algebra, geometry, combinatorics, and number theory. And the main reason for this is because these 4 areas are the most important thing. Like any sort of knowledge in these 4 areas has to be 100% down, because the AMY is not about applying applying only one of these. It's about applying all of them in succession. So if you have one loose link, you won't be able to solve a lot of these problems. So that'll be the first 4 classes. After that, it'll mostly be problem solving. Like I've said, the AMY is about direction. It's about experience. It's like you have and persistence, and these kind of things are built up through doing previous problems. And the AMY is also mixed. Like as you can see, there's no sort of like structure. Like, oh, here, I'll give you all the geometry problems first. So I believe that the only way you can learn to like adapt to this mix is to do mixed problems. So that's probably what's going to happen. I'm also most likely going to be adding like supplemental lectures, especially for some of the younger students who haven't taken things like trigonometry. Trigonometry does actually show up in the AMY. Some basic pre-calculus, and that'll be as time goes on, somewhere towards the beginning, obviously, because they're needed for these problems. But yeah, mostly start off with these 4 basics, 4 basic lectures on the 4 main pillars, and then supplemental, and then lots of problem solving.
Who are the people making this kind of AMC 10 or AMY problems? Year after year. Like the problem you just showed, the number 25. Out of his thinking that, okay, this is the problem I want to
Yeah, there's a committee called the MAA, I believe, and they spend their time making these problems every year. So right now they're probably already working on next year's contest. So they come up with a large collection of problems, and they just sort of sit and look at each problem and decide whether or not the problems actually focus on problem-solving skills versus simple arithmetic. Sometimes they get it right, sometimes they don't. There are a few problems. I was actually going to show an example of a problem where they may not have written the problem as well, but that